So I've already been introduced. This is a research concerning FDM technology and its use with fracture mechanic parameters. So the subject of this paper is the PLA and some different material called PLAX, which has a PLA matrix, but is different and has some different mechanical properties than original PLA. This is something, this was something concerning the technology, how it works. So FDM is an extrusion-based technology. I guess most of you know this part. So concerning this materials, so most popular materials in FDM are ABS and PLA, but still you can do something with the plastic and create some other material. You can do a combination of materials into one filament, you can add some second phase particles, or you can add some carbon or glass fiber additions to enhance the mechanical properties. One most obvious example of this situation is that sometimes PLA material is shipped in different colors. So they use different pigments, and somehow those are like these second phase particle additions, which not only just change the color of the material, but change even the nature of fracture. So some colors, some specimens with some colors fractured in brittle fashion, and some fractured with ductile type fracture. But all in all, they're shipping this as the same material, even though now it's not. Now concerning this PLA and PLAX, the PLA material we have fractures in so-called quasi-brittle manner. So this is how the stress-strain diagrams look for this material. They have, all 5 specimens had similar results, so there is a good repetitivity of the results. But this PLAX material has lower UTS, but much higher plastic deformation than original PLA. This is how a fractured specimens of PLA look like. They fractured in brittle manner, though this PLAX had this stress whitening region, so-called crazing, in this material. That's why it has greater plastic deformation. Now what we have conducted, so we used some printing parameters. We did some variations, so we used different layer height, printing orientation, and different percent of infill, and also we used some specimens which were dried before testing. Okay. And we had some 5 different batches, and we had the variation in layer height, as I said, density, printing orientation, and filament drying. Only 2 parameters were used, like for layer height 0.1, 0.2, for infill density 50 and 100, just not to use too many specimens, different orientations like circular and rectilinear. And just one batch was previously dried, so this first and 5th batch are deferred just in this filament drying. Now here are some results from the previous VCF conference concerning the tensile tests of PLA and PLAX, but you've seen the stress-strain diagrams, and that's most about them. So we created SEMB specimens for fracture toughness assessment tests. We used 5 specimens, 3 were mandatory, 2 were used as a replacement. In bulk, these specimens were like 13 by 26 by 114 millimeters, and the models were created according to standard. They were printed in that fashion that the biggest surface was placed on the platform, and that's how the specimens were created. Here are some finished specimens of this PLA and PLAX material. Now, we had to create a pre-crack. Of course, we used a hammer. We used a blade, and we used a hammer and made a pre-crack with this razor blade. With here are some dimensions of this blade, and the strain rate of this test was 5 millimeters per minute, according to standard. And also, as addition, we used the DIC camera to see the deformations on the front side of the specimen, and as a result, just for this presentation, were this deformation diagram. So one measures strain relative to this created section. So on the ligament of each specimen, we created 5 sections, like virtual strain gauges, where we monitored the deformation on the ligament side of the specimen. All right. Now, here are the force displacement diagrams. All the full infill density batches had a greater force value than any other specimen batch, but this difference is that in tensile tests in circular printing orientation, there was the highest force value, but here, due to different load direction, the rectilinear orientation had greater force value than in circular printing orientation. Now here are some deformation diagrams. We see that in specimens with 50% infill density and 0.1 layer height, created on this deformation diagrams, created so-called candle-shaped curves. Now here it shows that on the middle side, where the notch is and where the pre-crack is, and where the crack should follow a straight line, we have highest deformation values, and not on the left side, not on the right side, right-hand side, we have any deformations left. So probably this specimen will have a crack propagation in a straight line, like forward from the pre-crack to the imminent failure on the ligament. Comparing to 100% infill density batches, here we see lower deformation values, but much higher scatter along these section lines, showing that there is some deformation on the sides of the expected crack propagation path. So probably these specimens will have, could have some angulation in the crack path. Now comparing to 2 other specimen batches, which also have 50% infill density, which also have 50% infill density here, but differ in layer height. So the 4th batch has a higher layer height, and this 5th batch is dried specimen. They also have, so this is PLAX, no, sorry. This is the one. So here we have higher value scatter on the left and on the right hand side. So the best results according to the straight crack propagation path will be in the batch with 50% infill density and 0.1, so the lowest layer height. Also in some full infill density batches where the direction of printing was perpendicular to the printing direction, we also had some stress concentrations, so there was some kind of a delimitation between layers, and it created this high deformation concentration here, and we captured it with one section. So one section just crossed this concentrator. We've monitored the value, and as you can see how it affects on force displacement diagrams, you see that you have some incline. So this is how it affects on force displacement diagram. So because of this, according to standard, this test is invalid because there is force peak before the major peak. So this is also how some printing parameters may affect on test failure. Now with the PLAX, same story, but the force values are a bit lower. Also in rectilinear orientation we have higher force value than in circular because of the load direction. Then the deformation diagrams, also similar story as with PLAX, but now the fourth and fifth batch, so the batches with lower infill percentage, have don't differ that much from the first batch as the PLA did. So this is a ductile material, and also in the full infill batches we have a higher deformation value scatter. Now to see here also there was a minor issue with the same batch on this PLAX material, but this force peak wasn't that critical as in the PLA material. And just to conclude, sorry for this skipping of slides, I don't know what's the problem with my presentation. So we did fracture toughness assessment tests using also the DIC camera set device. We used 5 different batches of PLA and this ductile counterpart, so-called PLAX material, and we concluded that with full infill specimen batches, okay, there will be higher deformation value and, lower deformation value, but higher scatter along selected sections. So we created few sections on the ligament side of the specimens to capture the deformation values. We've seen that most probably the straight path, crack propagation path, will be in the specimens with lower infill percentage and higher layer height, producing on the diagram this candle-shaped curves. So in the middle part where we expect the crack to propagate, we'll have the highest deformations, and on the sides we won't have almost any. Also in both materials with different infill batches, different specimen batches with same percent of infill but different layer height, and okay, one specimen was previously dry. We had a slighter scatter on the sides compared to this first batch. This is most probably due to lower material bonding, because with higher layer height you will have a lower surface of connection between two layers, and also with filament drying, material then is shrinking toward the center. I mean, the filament is shrinking toward the center, so between two different layers you'll have lower surface of contact between them, and that's also why they cause some deformation value scatter along the ligament. Okay, because okay, the PLAX material is ductile. This is some material from Mitsubishi Chemical, and the problems in the PLA material were not so obvious in the PLAX material due to the ductile nature of that particular material. So sorry for skipping these slides. Thank you for your attention, and
okay. Any question from the audience? No one? Just my curiosity, how do you pre-crack the specimens?
yeah, I've shown, sorry. The pre-crack was done with a razor blade, and we used the hammer. We tapped the hammer onto a blade, placed in the notch, and to specific length. So the pre-crack was according to standard, and of course this hammer tapping on a blade was also according to the standard.
And which is the minimum ratios of the crack?
It wasn't specified in the standard, but the radius of the crack here, let me just open the slide. It's here. The blade was 2 millimeters long with a angle of 140 degrees, and well, the radius should be like 1 mil. I think
0.5. 0.5.
0.5 millimeters in radius.
Other questions for the audience? No one?
Can I just one?
Okay.
When did you dry the material? Before printing or?
No. After printing, but before testing.
Okay. Maybe before printing, maybe it's interesting too.
Well, okay, you're okay. It's already treated in the extruder on 200 degrees Celsius or so. This was done afterwards, just to see. Okay, you have a full specimen, you have a full structure. Now, when you dry it, of course, okay, different strands. Yeah, strands. They tend to shrink. They tend to shrink over their center. And when you look at two adjacent layers, you'll have, lower surface of contact between them. And that's why we dried them before testing, to see the influence on the full structure.
Okay.
Thank you very much.